bearing system contains 5 subsystems: the distance sensors, the displacement controller, the current control loop, the IR receiver, and the battery power supply. These 5 systems, in tandem, allow the bearing to float underneath the steel plate at an adjustable distance and to switch between float and lock mode. The distance sensors provides feedback about the position of the system to the displacement controller, which also receives inputs from the IR receiver about the desired position of the system. The displacement controller outputs commands to the current control system, which allows the magnets to draw the correct current. Finally, the battery system supplies power for all of the system's components. It requires a voltage regulator for supplying power to the TEVA. Here is an expanded view of our Simulink control components. Each electromagnet and distance sensor pair has its own control loop. First, we'll zoom in on the IR receiver subsystem. We used an infrared receiver in conjunction with a standard DirecTV remote in order to give commands. 3 buttons on the remote are used to do one of 3 things: increase distance from the steel plate, decrease the distance, or change between float and lock modes. The maximum distance is 1.5 millimeters, and the system is restricted to a range of 0 to 1.3 millimeters to ensure reliability. In lock mode, the magnet attaches to the steel plate and remains there until unlocked. In transition from lock to float, the magnetic bearing returns to the distance to which it was previously assigned. A simplified version of the displacement controller for one magnet is now shown. This Simulink model is executed from the TEVA and is a lead compensator based on a linear approximation of the dynamics in the system. The controller calculates the difference between the distance sensor input and desired displacement, and uses a discrete time transfer function to calculate the necessary current to correct the position error. The output is a voltage duty cycle percentage for a PWM in the current control loop. This controller is constantly increasing and decreasing the amount of current supplied to the electromagnet to hold the system in a hovering state. The control of the current drawn by each magnet is accomplished by this circuitry. An op-amp with a feedback loop exhibits a 1-to-1 relationship between voltage supplied to the op-amp and current drawn by the magnet. Therefore, the circuit can produce any current from 0 to 800 milliamps simply by changing the duty cycle of a PWM from 0 to 22%. The system has 2 11.1-volt lithium polymer batteries connected in series to provide 22 volts for the system. They are hardwired to a switch for safety and to provide convenience for activating and deactivating the system. The batteries are recharged through easily accessible connectors.